What is the history of neuroscience? What role does philosophy play in our understanding of how the brain works? In this recent interview with Athanasios Bourganos, also known as Cognic on YouTube, we discuss these fascinating questions. We also touch on free will, how to think about neuroscientific findings, science communication, and generally how the brain works. Athanasios Bourganos is a neuroscientist and content creator through his YouTube channel Cognic, which I'll have linked below. He wants to improve the public's understanding of neuroscience and the human brain via digestible videos that anyone can enjoy. He received an honors Bachelor of Science with a focus in neuroscience from the University of Toronto in Ontario, Canada. He currently works as a researcher in the Mac Lab at the University of Toronto. He recently developed a data visualizer for a project called Hip Circuit, where he and the project lead are trying to create a tractography atlas of the human hippocampus. It's really fascinating stuff. You can check that out on his website or on the lab's website, which is linked below. Now, without further ado, I give you my conversation with Athanasios Bourganos. Maybe you can just give us some background on who you are and why you decided to study neuroscience.
Yeah, sure. So my name is Athanasios. People call me Athan. I was born in the States. My family's from Greece. Dad was a doctor, so he was the one who told me don't get into medicine. It's stressful. You're liable for a lot of stuff. And he said particularly it's definitely a field where if you want to be a doctor, it's because you want to prescribe medicine or do surgery, but everything else you can do through academia, through research. When I was choosing what to do in university, I started computer science. So I was a programmer for the first little bit. And then I had loved programming before that, decided that my passion was draining. So when I started doing it for school and I had assignments that were all programming based, I stopped programming for fun and for leisure. And I had always been interested in going into some kind of medical research, but neuroscience stuck out, and I joined the neuroscience program and started programming again for fun. And now I program for a neuropsychology lab, and my research is involved with what we're doing in the lab. Do you want me to go into?
Yeah, sure. Yeah, that's great.
So in the lab, I'm working in the Mac Lab at the University of Toronto, and what we do is a whole array of memory and hippocampus stuff. My particular project is with a graduate student who is doing connectome mapping of the hippocampus. So we have a lot of connectome maps in the Human Connectome Project. People take the tractography of the brain, so where all of these like neuron wires all sort of string together, and they try to map out how the brain is connected. And what we're doing in particular is trying to figure out how the smaller parts are connected. So it's easy to see where big tracts go along the side of the brain and how the overall brain is connected. But when you zoom into something as small as the hippocampus, which is, only something like this big, how do you actually map out the wires within such a small space when the resolution on your scans is so small? So that's what we're working on right now, trying to scan really small parts of the brain and see how they're wired up.
Oh, wow. That is amazing. So how does, I think a lot of people, it might be hard to imagine, how does programming fit into a research program like that?
Yeah, so I think programming is a useful tool for any field, in my opinion. I think that one of the things that I would stress for especially people who are just in high school or even before high school is to start learning programming, whether it be through a school program that you have or through YouTube. I learned programming on YouTube. I learned Python. It's an easy language. And it's one that it has a lot of applications in medicine and in neuroscience in particular. So I think that for any field that you get into, if you're a writer, learn programming because you can find some really interesting things. But one of the first things I programmed was word counters, and I would download like the whole text of Moby Dick and by Herman Melville, and I would just run little analyses on it, like how many times does the word Moby appear in this book? How many times did the writer follow this word with this other word? And I just think programming is a good way of processing the world through like a different lens.
Mm.
So if you're a musician, you can use programming to look at 1,000 different songs and quickly tell you what the average tempo is for the songs that made a certain amount of sales or something like that. For
Wow.
writers, you can figure out like the speed at which you should switch topic in a book. For statistics, it's obviously useful for like analysis. For research, it's super important. And for me, it's important in neuroscience and for a lot of neuroscientists because of imaging. So we get a lot of our data through MRI. At my lab, it's neuropsychology. So pretty much all the data we get in is MRI data or fMRI data. And these are images, and you have to know some level of programming to be able to like open these images up, pull the data out of them, and then run analysis on that data. There's a lot of programs that do it for you. So a lot of people in the lab don't know programming. And one of the reasons that I'm in the lab now is because I'm helping some people to like pick up some programming. I'm doing some programming myself. But one day these standalone like programs, they don't do everything that you need them to. So you have this software that can run this analysis that's been done for like 10 years or 20 years. And then all of a sudden you need to take it a step further, but there's no command for that. There's no button for that. And this is where programming becomes super important because you need to understand how to open this file yourself and then do that extra stuff that the program just wasn't written to do.
Okay, yeah, that totally makes sense. And so I want to return to some of your research.
Yeah.
But what drove you originally to start a YouTube channel?
Yeah, so I have always been interested in YouTube or like creating content for YouTube. When I was a kid, we used to make funny little videos and upload them, and I really liked the YouTube sort of like idea or like the community, I guess you could say, without being part of like a. I don't talk to a lot of people on YouTube, but I have a few friends who do YouTube stuff, and my cousin does statistics, and he was making tutorials on YouTube. I actually started making programming tutorials on YouTube a long time ago.
Oh.
And yeah, and that was kind of how I picked up the whole bug for, okay, I can record my screen, I can do the programming I'm already doing and just record myself doing it, teach people how to do little code stuff, and then upload that. And it got some attention. And I realized after I was almost done with my undergraduate career, and getting my neuroscience degree, I figured, neuroscience is really interesting. And I'm shocked at how few people know what it is, because people can kind of parse the word. Like you'll say like, oh, well, what do you study? I study neuroscience. Oh, so it has to do with the brain. And I'm like, yeah, it has to
Yeah.
do, we everything, like everything brain related, we look into, like, but there's also philosophy in it. And there's also, a lot of computer science. Mathematicians help with neuroscience. And so I explain it to people and they go, wow, this is incredible. I can't believe I haven't heard more about this. And I realize it's because there's a huge barrier to entry for neuroscience knowledge in the sort of like public space. And one of my professors, actually the one whose lab I'm working in, brought it to my attention that there are a lot of articles out there that completely ruin the field. Yeah, like, and that might sound extreme, but there's a lot of, you'll go on the news, and the way the news perceives neuroscientists is scientists have found where love is in the brain. we now know why you love. And people get all excited and they read the article and it says you love because of this particular part on the right side of your brain called the insula. And you go, okay, awesome. But that's also the part of your brain that activates when you hate someone or when you want to, if you're in a fight, right? Like your insular cortex goes off. It just means arousal. It doesn't mean love. It doesn't. So you'll have these articles coming out where it just misleads people completely because of that barrier to entry of people understanding how to read these papers. There was a famous case and a TED talk about it where a female researcher said something along the lines of she did a study about the insular cortex, and articles were written like, you love your iPhone the same way you love your spouse. stuff like that. And like grilled cheese sandwiches activate the same part of the brain that the person you love activates, or something like that. And it just, I just realized that people don't know how to read some of this information. And I don't even know how to read some of the more advanced information if it's not in my niche. So if I read neuroscience papers from you did cellular stuff. If I was reading papers that came out of the lab you were in, there'd be a barrier of entry for me. I'd have to learn how those analyses work and how that data is looked at. I wouldn't be able to just come in and read that paper and then parse it.
Yeah,
So
likewise.
part of the reason that I think it's so important to do these kinds of channels, and why your channel is important as well, is because someone who's in the field has to say, okay, let's put this paper in a more digestible format, or this information in a more digestible format, so that if someone wants to write an article, they can, but they know how to do so in a way where they're not going to accidentally mislead people. Because I don't think it's malicious. I don't think it's intentional. I think they see a paper, they read what they want from it, they get excited, and they publish. And they, I'm going to write a cool article about how you're in love with your iPhone. And it's like, well, one day you're going to realize that that's not what that paper meant. And people are going to think you were just trying to be sensational. But I think I try to give people the benefit of the doubt. I think it's excitement. I think they read it, they get excited that they think they understand it, and then they write about it, and people get the wrong idea. I think so. That's one of the reasons I started, is just to try to clear up some of the gray stuff, and then also just give people cool inspiration, I guess, for things that they can study. Because I think neuroscience is one of those fields where you can kind of study anything. Everything is done with your brain. And so if you study the brain, you can study anything, really. If you like writing, you can study neuroscience and then study how writers, write, and what parts of the brain are important for, text to speech, text to text. Like what do people do when they process, or when they're creative, when they're like processing writing? Anything is applicable to neuroscience, I think.
Right. Yeah. Yeah. And just on that point about bad articles about neuroscience, I don't want to put it all on journalists, but I did a brief stint in journalism school, and I can definitely see that the incentive for writing an article fast can be a source of that kind of like inaccuracies. It's just like the timeline that some of these, especially the daily science writers, science journalists, are like, the pressure they're under to get a story out, to just get more and more stories. It's publish or perish, like taken to the extreme. So I think they have some pressure on them, and then, they get this article out, and maybe it's not perfectly accurate, but maybe they feel like it gets the point across. But as a neuroscientist or neuroscience enthusiast, someone who's really into the science, looking at it, it can just be like a facepalm moment,
Yeah.
Yeah.
I think that there's a lot of things that, and like I said, I'd like to give people the benefit of the doubt, because I don't think anyone wakes up in the morning and goes, I'm going to lie to everyone about neuroscience. Like, I don't think that that's like the intention. I think that it's what you said. It's churn. These people go to work and they have deadlines, and they have also news comes out, and it's not news for long. And so this paper drops and people see it and they freak out and they go, I need to write something on this really quick, because by the end of the day, everyone else is going to have written something about it. And recently a paper came out, actually, that was all about how there's these big studies in genetics, these genome-wide association studies, where they look at all the genes that people have and try to correlate them with certain conditions. So if you have, cystic fibrosis, we look at everyone's genes who has cystic fibrosis. Can we figure out what the gene for cystic fibrosis? And they have a lot of luck with that. It's a really good method for gene analysis. But recently people have been trying to do these brain-wide association studies. And a paper came out, I think a couple of weeks ago, that was just, the idea behind the study was, if you want to do brain-wide association studies, you can't use 30 people. You have to use thousands of people.
Mm-hmm.
If you want to get meaningful results. And this was kind of a big deal for a lot of people who do brain-wide association studies, because for a lot of those people, they only have 30 or 50 participants. And so it's kind of like saying, sorry, you have to redo all your research because
Yeah.
actually it might not mean anything. But people wrote articles about it. And one of the articles that was written about it actually asked the guy who wrote the paper for a quote. And he said something along the lines of, I remember looking at the results and my jaw dropped. And I realized that like the field was changed forever, or something like, some dramatic sort of, and everyone started tweeting about it, neuroscientists saying, what are you saying like about fMRI research and about DTI research and all this stuff? And he even went on Twitter and said, no, this doesn't affect any of you. This is just for the niche group of people who do this particular analysis. And it was a lot of that anger in the field was because of the sensationalism of, oh, this paper I've been told this is a big deal. I'm going to write something about it. I have to make it dramatic.
It's a juicy
Otherwise,
quote.
juicy quote. And it was the wrong juicy quote, and
Yeah.
it made a lot of people upset. And he had to go clarify, one of the authors, to a lot of people, like, this doesn't apply to you. Your research is fine. Just this very particular analysis. And it was, I think it was a misunderstanding again, but it all comes down to that intersection between there's science, and then there's writing about science when you don't have like a huge amount of scientific training, and the problems that can arise with that disconnect. And people do their best. I give, again, people the benefit of the doubt, where they're not trying to mislead anyone. They're trying to get people excited about something that not a lot of people are excited about. The problem is that in doing so, sometimes they embellish to the point where it's no longer like the actual essence of what was originally studied or something like that, right?
Yeah, definitely. Definitely. And something you said earlier, I think it's, you were talking about how there's all these different ways of approaching neuroscience, all these different ways of looking at problems in neuroscience, coming up with ideas for studies. Like you were mentioning writing, we can think about how does language processing work in the brain, or really anything. And you and I were kind of talking before we started recording about the fact that kind of the history of neuroscience is filled with people from all different kinds of disciplines coming in. And I thought we could kind of jump into a little bit of the big history of neuroscience and talk about how it's different from other fields and how it has developed in kind of the broad sweep. And so just take that however you want. We can run with that.
Yeah, sure. I mean, I think one of the interesting things about neuroscience is that it is the science of us. So it's we, as human beings, like any other animal, our whole conscious experience is because of our brain. We have the body that we walk around, not to give everyone an existential crisis, but the body that we walk around in is sort of like a vehicle for your nervous system. And so I always kind of joke around with people and say we're like jellyfish in mech suits, because you have this really like sensitive, delicate nervous system that just is kind of in this big suit that carries you around, and you have some like sensors, you got some cameras, you have a chemical detector right here, you got some like audio detectors, another chemical detector in your mouth, your tongue, right? So you have all these different sort of sensors to like learn about the world. And neuroscience started off in like prehistory as being, it was philosophy, and it was what everyone had different theories of, where does this whole existence come from? Is it centered in your heart? The heart is the thing beating and moving, and so maybe that's where it is. And some people thought our soul is in the fluids of our body, but it wasn't until sort of antiquity where neuroscience transitioned from just being about philosophy to being an issue of how do we fix problems medically. So it was responding to damage. It wasn't so much discovering new things about science as it was, I was in a battle and I saw someone get hit in the head with their sword, and they fell on the ground, and now they're shaking uncontrollably. And for us, we see someone shaking uncontrollably nowadays and we say, oh, it's a seizure, because we know it's common knowledge now what a seizure looks like. But back in the day, it was probably pretty easy to look at a person shaking on the ground and be like, oh, don't worry, they're just talking to the gods. You know what I mean? They're being visited by some sort of spirit, or they're possessed. So neuroscience quickly turned from just philosophy of, what's all this, to, okay, I was in a battle, I saw injuries, I need to fix these injuries, and now I'm starting to make connections between certain injuries and certain outcomes. And I think in my history of neuroscience videos, one of the first things I talk about is the Edwin surgical papyrus. So this is like all the way back in ancient Egypt. It's a military doctor who has written down this wonderful script that's preserved to this day about, I saw a man get hit in the head with this weapon, and now he is shaking. And when I cut a hole in that same place where he got hit and I relieved the pressure, this was the outcome. He lived. And, or if they didn't live, this was what happened before their death, after they were hit. Maybe they did live and they had like some issue. And he writes about that. A lot of the soldiers who were in the battle, even if they didn't get hit, they still shake, right? And he starts noticing things that are psychological, like PTSD. And so it did go from the philosophy of what is existence to, now I'm seeing actual people get hit in the head and things are happening to them. Let's start writing down these cases. And now we move into where it starts getting interesting, because people then see that as an area that they can start to explore. And you have a lot of people from ancient Middle East, ancient Greece, ancient Roman Empire, right? And you have all of these different doctors who, and generally they were doctors, who were saying, if you have your prisoners, let's say, I think it was the doctors of Hippocrates' time, and they didn't like cutting people open. That was like the human body is sacred. You don't go chopping people up. It was only after that sort of camp where people said, okay, well, you can chop up a prisoner. You know what I mean? Like that, like, okay, there's some people you can chop up, or if they're dead. If they're dead, we're not supposed to desecrate the dead, but if you promise it's important, you can start to look inside people. And that's really when neuroscience went from, again, philosophy to doctors trying to fix problems and take note of injuries. Now it gets into physiology. So now we're actually like dissecting people, trying to actually name things. And that's when it explodes. After that is, we now know, well, here's all these nerves that we've now named. We don't know what they do, but we know where they connect and we can name them. And now when people come into the hospital and they have that nerve cut and they lose a certain function, now we can actually write down, when you cut this nerve, their hand doesn't work. I'm going to make the assumption that cause and effect, this nerve is what controls the hand.
And now we're talking, like, sorry to interrupt, but like 1700s or so. So we've kind of zoomed in through the antiquity into
the thing is, and again, another difficult part of the history of neuroscience in general is that it wasn't so much. There are themes. So just like you said, there are themes where, the 1800s was a huge explosion for this type of research, for like lesion studies, let's say. But a big thing is that a lot of these like philosophers from even antiquity had these ideas, and were quickly either shut down or ignored for hundreds of years, until people later went, oh, they were onto something. I think there was one guy in particular, and I'm going to forget his name, and that makes me a bad Greek because he was one of the Greek guys. But there was a natural philosopher who was pretty aware, unlike the other doctors of the time. No, the soul and the mind doesn't exist in the heart. It's in your head. It's in your brain. And he said this somewhere like, we're talking like 500, 600 BC. Who just realized, okay, I kind of figured, I think this is pretty important. Other people hundreds of years after that still said, no, the brain is just this thing that cools down your blood so it doesn't get too hot. It's like your radiator. And totally ignore it. So there are these ideas of, there were people who did, like actual connection studies and said, I actually think that this nerve affects the hand, but this happened so long ago that people looked at them and kind of went, yeah, sure. And
Yeah.
ignored it for 500 years. So, but you're right. I think most of that 1700s, 1800s is when people really started to push through that sort of initial, this is just physiology and medicine, into actually there's more going on here. We can actually start to look at, I mean, Swammerdam uh,
Hmm.
starts doing a lot of this like biology work, and I'm totally lacking on the dates, but actually looking at microscopes and looking at cells, and particularly noticing like there are discrete units here. Like there are, it's not just that you have a nerve running down your whole arm. Now that nerve has been segmented into cells, right?
Mm.
And then it took another couple decades before people said, yeah, but it's not just one type of cell. There's multiple types of cells in here. And then another decade when people go into that and say, and even within these groups of cells, there's variation. So I think it's just like an increase of, the history of neuroscience is an increase of complexity.
Mm.
It's, we are a thing, we're a body and a soul, let's say, if we're like Descartes. And then you move past that to, okay, well, let's say that we're a body and a soul, but we do have this like nervous system, but it's just a nervous system. Well, now the nervous system is made of cells. Well, now these cells are different classes of cells, and the nervous system has now been split into three parts. Now it's not just the nervous system, it's the central, the autonomic, the peripheral nervous system. So you're switching from, you start with this like monolith of like nerves, and you split it smaller and smaller as history goes on. But yeah, I think, sorry to answer it like in a really long-winded way, you're right. It was about 1700s, 1800s where people really buckled down and said, okay, maybe we should stop focusing on just naming things and we should actually start looking for function.
Yeah. That's a really interesting way of characterizing it, like the broad sweep of the history of neuroscience. So where would you say, like, if it's just increasing in complexity, where does that land us now? I mean, how would you, if you had to put kind of a label on our current period of neuroscience research, what would you say?
Well, so yeah, this is definitely, and I don't want to like upset a researcher ever, but I think one of the problems with humans and like and our brains actually is that we are a type of, we're a system, we're like a technology, almost a biological technology, and we've modeled a lot of AI off of humans. So neural networks are based on the idea of like perceptrons first and then neural networks. We're all based on the way our brain is wired up. One of the problems with neural networks that we've discovered, because a neural network, the nice thing is you can train it 10,000 times in a day and get some results back about how that went. And what we know about neural networks is they overfit.
Mm-hmm.
And I think humans are prone to this same issue of, when you overfit a neural network, you train it on a data set. Let's say you give it a bunch of pictures of cats and a bunch of pictures of dogs, and it learns to recognize cats versus dogs. If you show it new pictures of cats and dogs, if you've overfit your network, it won't do well, because what it does is it says, okay, I've memorized each one of the dogs that you showed me before. And so I can tell you whether or not it's a dog, not based on the picture, but because I've seen that exact example before, and I remember what the answer is. And humans are like that too, I think. And so one of the dangers we have in neuroscience research nowadays is that we've built on such a large, grand foundation that we start to sort of limit ourselves with the complexity. So as neuroscience gets more and more complex, we tend to sort of get stuck at this sort of like maximum of like, I think one of the big issues of the recent couple decades was our dependence on like computer models. So we have based a lot of our neuroscience thinking nowadays on going, oh, the brain's like a computer. But computers came after us, right? So like computers were built by brains, not brains built by computers. So for us to say, oh yeah, computers and brains are very similar. I totally agree that there's similarities between brains and computers. And I'm a big fan of that camp of the computational side of neuroscience. I do think that it does tend to limit us a little bit in where we go from here. So all of this previous grand work on figuring out neuroscience was great because a lot of it was measurable. So how fast does a nerve fire an impulse? That's something you can actually sit down and measure the connection and measure the speed. How does this neuron connect to this neuron? You can look and actually check. A lot of this stuff was like very discrete information that you could actually just look at. A lot of our information now, and what I think is not bad for neuroscience, it's definitely interesting, but what's a little dangerous is that people depend more and more on information that we can't measure, we have to infer. A perfect example of that, I think, is like EEG research. EEG research was like the pinnacle of neuroscience research when it came out. Everyone loved EEG. But EEG measures the signals that are on the surface of your brain, like the electricity in your brain, but through the meninges, which surrounds the brain, through the skull, and then through the skin, and then sometimes through the hair.
Yeah.
And so these electrical signals, when they come off one part of the brain, go and they bounce around. And by the time they hit the top, you don't actually know exactly where it came from. And there are like ways to try to minimize your error and stuff like that. But the farther we move from looking at the actual brain itself, the more dangerous the things we infer sort of become. Because your picture that you're looking at imagine having a picture of like a scene, and the farther away you get and the more stuff you add into your program, the blurrier the image gets. You can still see stuff in the image, but the farther you move from the actual object you're imaging, the blurrier it gets, and the more you have to say, we think this, but the reason we think this is based on these 3 assumptions, now 4 assumptions, now 5 assumptions. And the farther you get and the more complex, neuroscience is moving faster than technology, I think, is the problem. Neuroscience is, we can't wait for the scanners to catch up. We're starting to do analyses right now where the scanners haven't even been invented yet. And when they're invented, we can test those hypotheses. But until that happens, we're just preparing for the future. I think that's sort of like a more succinct way to put it.
Wow, that's fascinating. Yeah, and just to tag on to a couple of those points, with the EEG thing, I think like just to kind of add another layer to that, I worked in a lab where we would implant electrodes like under the skull of mice for EEG recordings. And even then you have to make a lot of assumptions, and you have to be really careful about all the noise in your data, and be really, and especially with mice, you can't ask them what's going on, so you're also just, you're making a lot of assumptions there. But it's all the worse if you've got layers of tissue and hair and all kinds of stuff between it. And then kind of something that just popped in my head while you were talking about kind of the assumptions we make when looking at these computational models of the brain. Like I think the neuroscientist, I guess he's a neuroscientist, Jeff Hawkins, he wrote the book 1,000 Brains, and he's like a computational neuroscience AI guy. And he talks about how for a long time, just like the dendrites, the dendritic processes on neurons, were not even not even included in a lot of models of how neurons worked computationally. And I don't feel like I'm probably mangling all the jargon and everything here, but I mean, these are dendrites account for a larger surface area, I think, than the rest of the neuron itself. So it just kind of shows how, like you said, the technology is kind of behind, or maybe the theory is just ahead or behind or something. But anyway, I know that was a little bit of a crazy.
No, I totally get it. I would compare it to physics. I think in physics, there's a running joke where, and I'm not a physicist, so I'm going to get this wrong, but they usually make jokes in physics about, okay, so imagine you have a cow, but it's a spherical cow in a perfect vacuum, right? And it's like when we do science and when we do theory, a lot of it is based on these assumptions that are really funny, because if you want to calculate how quickly a car slows down on a road, well, realistically, you have to take into account how thick is the air, like what altitude are they at, what's the drag of the road, how smooth has the road become, like what about the tires, how long have they been used, and there's all these things. So physicists always make these like, okay, so imagine you have a car on a surface that's perfectly frictionless and there's no air, so it's like space, it's a vacuum, and the car has a perfectly efficient engine that doesn't make any heat, right? It translates all its power into motion. So we do the same thing in neuroscience 100%. Like you said with the dendrites, like there are models of neuroscience where they say, pretend that neurons are perfect lines and don't have any bends, right? And things like this are what limit us. And I think a really good quote by Alan Watts is that science is not reality. Science is like a model of reality. And so when you have a graph that says like, this is the temperature based on the time of year, it looks like crazy. The temperature changes all the time, and it looks really messy. And so someone can come along and draw a really smooth line through that and then say, here's my model to predict the temperature. But that model is always going to be just a little bit off from the real thing. And unfortunately, we've come to a part of history where everyone thinks of science as being this like perfect explanation for what happens. And in a lot of cases with like physics, it is really close to perfect. Like quantum physics, their measurements can go down to like 26 decimal places of accuracy or precision. For us, it's not that many. So we can't say with 100% certainty anything. We can get really close, and I'm not trying to discredit the value of science. I wouldn't be in academia or in science if I didn't think that it's valuable. But I think people have to remember that science is a way of explaining why things happen, but it isn't the things that happen. So science is like a good way to describe what's going on, but it's not what's going on. It's like our way of trying to make sense of the future and the past based on what we can measure right now. And sometimes we're really spot on, and sometimes we're really far off, but we tend to figure out how to make our answers better over time. They just shouldn't be conflated with the exact real thing. So kind of like with like looking at someone's brain scan, you can say like, this is the part of the brain that causes you to move your left finger. So, on the right side of your brain, some part of your motor cortex, on the right side of your brain, some part of your motor cortex controls your left finger. And you can show like some students a picture in class and circle a little part of the cortex and say like, that's the part. But in a real person, their brain's going to look different than the person next to them. And their brain is going to look way different than the person who's next to them. So you have to remember that when we have that map and we draw those lines, it's all it's squiggly. Like it's not going to be these nice perfect boxes on a picture of the brain. It's going to be way different in reality. Generally, like the average falls into that box,
Right.
but it's going to be slightly different for everyone. And I think people tend to think of neuroscience as like, oh, can you tell me why I do this?
Right.
And it's like, well, yeah, that's, I can give you my best guess.
Yeah.
But we don't know why you do that, because if we did, then it would be a lot simpler. You have 86, like people say 80 to 100 billion, but like, let's say roughly 86 billion neurons and trillions of connections, right? It would be really cool if we could say, yeah, the reason that you do that is because neuron A fires to neuron B, which fires to neuron C, and then it loops, and you describe every single part of the calculation, but that's just not fathomable.
Yeah.
So you have to make these averages, and you have to try to quantify like the unquantifiable right now with our current technology.
Yeah. Yeah. That reminds me, I was talking to Mark Humphreys, a neuroscientist who wrote the book, The Spike. And he was just talking about very similar line of thought, but we've been kind of almost cortex-centric in the last like 20 years of neuroscience, just because the tools that some of them that you mentioned, like EEG and especially fMRI, have been really, really good at looking at the cortex itself. But he argues that, we should be looking at the brain more holistically, and even something as simple as moving a finger. Yeah, you can circle the area on the motor cortex and say that's where it happened, but then you got to follow that whole cascade of action potentials and all these events all the way down to that finger. And that involves subcortical brain regions. And we know a lot about movement, about motor actions, but as far as cognition and emotion and things like that, the subcortical brain regions are definitely going to be important too. And he argues that we're kind of just entering this era where we're going to be able to start to look at some of these deeper brain structures.
Yeah, I totally agree. And I think people also tend to think of neuroscience in terms of, like you said, cortex-centric, because it used to be based on like things like EEG, and also even when getting more advanced than EEG, moving a finger, it's you can circle that part of the brain and say like, oh yeah, there you go, you moved your finger. But think about, as tasks get more complex, how many different brain regions must be recruited to do that thing. And people tend to think like, oh yeah, moving a finger is kind of like jumping up and down. Okay, sure. But now imagine eating an apple, right?
Yeah.
You have to move to eat an apple. You're actually tasting the apple. You have to control how quickly you chew. You have to think about when to swallow. You can't swallow when it's too dry or not chewed up enough. And there's all these different, another one would be like buying a house. I want to look and scan people's brains when they're buying a house. Okay, that's interesting. But when you buy a house, you have to look at the house. You have to go through your memories and figure out other houses you've seen in the past that it reminds you of, or parts of a house that you like. I really want a fireplace because when I was a kid, so now you go like back into your memories and you're doing all this crazy processing. And then you get to the math part. Okay, well, can I afford this house? How much money do I have? Let me go into my memory and grab that number. Let me compare it to the price I'm seeing in front of me. Now I'm comparing numbers. Now, if I were to pay this house, I have to do a down payment. It's 20% of the cost. Now I'm doing math, trying to calculate the down payment, calculate mortgage. Now I'm thinking of time. Now I'm going to pay this mortgage for 10 years. So buying a house is immensely complex. And people tend to think of like, okay, yeah, buying a house is an activity, but an activity can involve hundreds of different faculties and like hundreds of different processing streams. And so people tend to think like, oh, I want to study when people buy houses. I'm going to stick them in an MRI machine and tell them to look at houses to buy and give them a certain amount of money and do this experiment. But people forget there's not a part of the brain you can circle called the buying house part, right? It just doesn't make sense. There's a moving finger part, and maybe there's even like a calculating division part. But there's a lot more that goes into these more complex tasks. And I think another thing that I made fun of the brain-wide association studies for is they do a lot of studies where they look at everyone's resting brain connectivity and they try to tell, is this person a psychopath? That's like a big one. So a big question in research is, if we look at these like psychological metrics, and I'm not an expert in this, so I can't comment on like the validity of this data or like whether or not you can tell if a person's a psychopath based on their brain activity. But that's a lot different than figuring out if a person is right-handed or left-handed, right? These are questions that we can sort of have a person do tasks and we can make good guesses about. But something as complex as psychopathy or sociopathy or one of these more like pathological sort of like brain states, I mean, these things aren't 1 or 0. There are some people who might be a 10 on the psychopath scale, and others might be a 7, and others might be like a 3. And it's very difficult to take something as abstract as psychology or like some big psychological class and then distill it down into, okay, so what does like a psychopath's brain look like? Because it can look like a lot of different things. Everyone has a slightly different brain. One of the things we learned right when getting into fMRI studies or fMRI data is that it's super stressful when you see people's brains, because when I see a picture of your brain, it looks weird to me. I can be a neuroscientist who has seen 1,000 brains, and I'm going to find some part of your brain scan where I'm like, what is that? Like that part of the brain looks so odd. I've never seen someone with a frontal lobe that looks like that. And it'll stress me out. And then I'll ask my supervisor, is this like normal? Do I have to call the radiologist and tell them to warn this person? Yeah, don't worry, that's fine. That's fine. Or you send it to the radiologist and they say, no, that's fine. And even seasoned professors who have been doing this research for years will see people's brains and go, there must be something wrong with this brain. And they show the radiologist and the radiologist goes, no, some people just have really small ventricles or really big ventricles, and these things there's so much variation in what a normal brain looks like. Two brains might look wildly different and yet be perfectly healthy, normal brains. And so it's really, really difficult to then look at these really wildly different brains and say like, oh, just by looking at this brain, I'm going to try to tell if this person's a psychopath or if they're in love. Or, these complex emotions that, is this person creative? I don't know. Creativity is really complicated. It's not something that you can it's not like a moving your finger kind of thing, right? So I think that's another sort of difficulty that we have in neuroscience, and something that, like you said, with cortical-centric thinking, is if I look at this person's cortex and how much gray matter they have, I'm going to try to tell if they're this. And it's a dangerous way of thinking only because it limits you to trying to distill a lot of really abstract, complicated emotions and tasks and states into this like binary sort of like, are they or aren't they?
Yeah.
Kind of problem. It's difficult.
Yeah. That's just a fascinating set of issues. Speaking of trying to distill something very complicated and almost philosophical into a simple answer, I kind of want to zoom out a little bit and talk about some more. We're circling around philosophical issues. We're talking about kind of the philosophy of neuroscience, and so. All right. Well, I'll start with this one, because a question that I've been posing to all my neuroscientist guests, anyone who studies neuroscience in any capacity, is can you give me a elevator pitch type answer to the question of how the brain works? Meaning just a short.
Super short. Okay.
Well, and
That's
it could be long. If you want to elaborate, go for it.
Well, I talk a lot, but I'm gonna try to distill it down. But I am a talker. Okay, here we go. Here's my elevator.
It can be a long elevator ride.
Okay. We're going to the top floor. Yeah. So the brain is an emergent system. So if I give you a discrete little agent and a couple of rules, it's not that complicated. So imagine an ant. You have a little ant, and the ant has a set of rules. There's 3 types of ants, let's say. There's soldiers, there's nurses, and there's builders. These are our 3 ant types. And I say to the ants, okay, here's your rules. I want there to always be a third builders, a third nurses, and a third soldiers. So go around and sniff all the ants. And if you sniff one of the ants and you figure out that it's a nurse, add 1 to your nurse count. So you keep track of how many nurses you see, how many builders you see, and how many soldiers. If you notice that out of all the ants you smell, about a third of them are nurses, a third of them are builders, and a third of them are soldiers, do nothing. But if you notice that there's more builders and soldiers and not enough nurses, I want you to switch your job and become a nurse, right? That's the rule. So it's not too complicated. There's 3 types of ants. Make sure there's a third of each of you. Go around and sniff each other. And if there's less of one group, join that group so that we keep everything at a third. Perfect. That is like a simple little rule for 1 ant. Now, put 10 ants in a pile and let them do that. Put 100 ants in a pile and let them do that. Put 1,000. As you put more and more ants, more complex behaviors emerge. And that's what emergence is. And a perfect way for someone to look at this is like the Conway game of life, right? When you see these little like discrete pixels and you give them a couple of rules and then you let them go wild and they evolve into these crazy systems. In my opinion, as a neuroscientist, the brain is an emergent system. You have neurons are the discrete little units, and there's other discrete units in there, but for simplicity, like neurons. You take those neurons, you give them a bunch of rules. This is when you fire. This is when you don't fire. This is how many receptors you have to fire. And then you make 1,000,000 neurons and stick them all together. Or you make 1 billion. Or in our case, you make 86 billion, right? And you say you can connect to this many, like these are your simple set of rules. That's how the brain works, in my opinion. It's an emergent system of tiny discrete parts with a simple set of rules, just multiplied to a really big scale. People sometimes say, like, what's the difference between me and like a cow, brain-wise? And generally speaking, the brains work the same. It's the amount of neurons and how they're connected up. And so you can go from goldfish to human, and not to say anything against goldfish. I'm not like, you can be human to goldfish. I'm not labeling the spectrum, but what you're really varying there is the amount of neurons and how they're connected. And so in my opinion, the brain is an emergent system. That's like the most succinct sort of like way to put it. Is that too much are we at the top?
That's that's good. That's shorter than some other pitches I've heard. No, that's great. Okay, well, now on to an easy question. So we're kind of talking about all these philosophical issues surrounding neuroscience, and I think one of the biggest ones that's on people's minds is, like, do we have free will? What's your view of that question?
An easy one. So
yeah, that's an easy question.
So a lot of theology throughout history has been separating humans from animals on the pretext that animals are like these robots that are sort of these like autonomous little beings that they operate just based on their impulses, but humans have this like very grand free will that separates us from all these other animals. And a lot of that was giving us rights to sort of do what we will with animals. And I think a lot of people needed that justification throughout history. So like, when it comes to things like farming and explaining to your child, like, Dad, why are we like raising up all these cows and then we kill the cows? And it's, okay, well, they're different. They're animals and we're humans, and they're like robots, but we have free will and we're these big, superior beings that sort of like have dominion over all of the animals. But I think now in a more nuanced sense, we all kind of understand that we are animals. And so this idea of free will, this idea that we can sort of like get over our impulses and do things that we don't necessarily want to do, but we want to do. A dog, when they're tired, will sleep, and when they're hungry, they'll eat, and when they're thirsty, they'll drink. Humans have this superior free will ability to be hungry but not eat if the food isn't yours. I have the free will to be hungry, and I see someone else has food, and I'm not going to run over there and steal the food from them and eat it because I'm hungry. I know that's their food. I'm going to go get my own. I'll wait. If I'm tired, but I have to do work, I'm not just going to fall asleep. I'll stay up. I'll force myself to do the work. But as I kind of alluded to, I think this is an illusion of free will rather than free will. So I think that everything that we do is based on a set of rules. When we talked about emergence and how the brain works based on these neurons that have little rules, and then as you sort of like add more and more complexity, the rules get harder to determine, but they still exist. I mean, we are kind of like robots in the sense that if you need nutrients in your body, when I get hungry, I think I mentioned this to you before in a different conversation of like the superior human being floating in like space of consciousness and thinking like, I am hungry and so I will eat. But it's not really like how it works. Your body requires nutrients and vitamins and protein. And so it says, hey, I'm going to send a signal that I need this stuff, that I'm lacking in something. And then your brain sort of like gives you these sensations of, your stomach is starting to sort of like move around a little bit. You're salivating in your mouth. And so your body has ways of sort of signaling what you need to you without saying it. You don't hear a voice in your head that says like, alert, you need more calcium. Like you just kind of get like this feeling of like, you know what I really want right now is some dairy. I want to eat some yogurt or something. Like I want to, and this is your body's sort of like natural way of providing for itself through these like impulses. um, I think a lot of our there are things that sort of people use as like free will examples. Like, well, what about something that's not good for your survival? Like taking a bullet for someone. Like you see someone who's in danger and they're about to get shot, and you jump in front of them, and that's not good for you. Like that's free will. You've decided to do it. But I think a lot of free will um, are these instincts that we have based on like altruism. And there's a lot of studies about evolution and altruism and how there's different types of ways that we can sort of like sacrifice ourselves that's actually for the greater good. So for example, you might think to yourself, if someone takes a bullet for someone, it's because they really don't care about their own life or anything like that. But really they actually do in a way, because if you jump and take a bullet for someone, you realistically know, you don't think this when you're doing it, but realistically it's an instinct in the way of, I'm helping someone, and me helping this person might not benefit me. The cost benefit might be really bad. I might die, but this person is going to see me, if I do survive, as being really, really helpful and really, really good. And they in turn are going to help me. And if I die, they're going to help my kids or my genetic relatives. They're going to help my family survive because I helped one of theirs survive. And so it's these instincts that we have built into us that at the end of the day all come down to like passing on your genes. And that's really like the sort of, people say, what's the meaning of life? Like, well, it's not so much that there's a meaning of life, that there is a way that life works, which is that you are born, you try to be a successful member of your species and pass on your genes. And if you do, then you did something right. And if you don't, then you did something wrong, or you just got really unlucky. But this illusion of sort of like of free will, I think, it's just like a grandiose sense of self. It's this idea of like, I must have free will, otherwise how would I be? People look for reasons why they should feel special. And I don't think that that's wrong. I think that people should feel special for a lot of different reasons. But I think looking for that sort of like special validation and thinking like, I have free will and animals don't, I almost think it's more beneficial or like more admirable to say like, no, I am an animal, totally. And maybe I don't have free will, and everything that I do is an equation being calculated in my brain. And while I think I'm making these decisions, really my body is making them for me, and I'm going through in this sort of like automatic path. But isn't that amazing though, that exists at all? So it's not so much that you should like, yeah, do I have free will? No, you don't have free will. Like, oh, well, now I suck. It's like, no, you're still like really incredible, because the fact that you exist and you're part of this system that is sort of like on its own, just this like propagating like emergent system that is life, like you're part of that, and that's really cool. You don't have to be like the sort of director of that system to be special. You can just be part of it and still be really, really cool. People spend like all day watching nature documentaries sometimes. Like a lot of people love nature documentaries. We have like Planet Earth and Blue Planet and all this stuff. And they spend all this time watching this stuff and going, wow, that is absolutely incredible. That's like the coolest thing. Did you see that, like that shark and the dolphin and did you see that monkey? Like, wow, it's so cool. Yeah, I'm not part of that though. Like I'm better than all of that. I'm like I'm something else. And then there's all that cool stuff. And it's like, no, you're part of that cool stuff. But we need to embrace it a bit more. I think we should put more emphasis on making documentaries about people, but less so about like the higher level, like here's a documentary about like this guy who committed a bunch of like Ponzi schemes, and like we're gonna do this like this big like op-ed on like this guy. It's like, no, like maybe do some like basic videos about like some basic documentaries about like, hey, this is like people just doing what they do, and how cool is it that they do this set of things. Just like dolphins have these social behaviors, look at these human behaviors. If you ever see a person, I found this out when I took an anthropology course. Sometimes people will like nervous smile, or they'll kind of like grimace. They'll go. Have you ever
Yeah.
seen someone do
Yeah.
that expression?
Definitely.
Like a
Absolutely. Yeah.
yeah. So that expression, right? If you watch any primate documentary, is a sign of anxiety in primates. And when primates grimace at each other, that's them. They do it more obvious. They go, right? But people do that all the time. And they do little things like that that they wouldn't even notice. For them, it's just, I'm just behaving. But
Mm.
that behavior can be observed in all of those other animals that people separate themselves from. Um, Dolphins do recreational drugs, right? They bat around pufferfish that have little amounts of neurotoxin in them, that like tetrodotoxin. Like they will like bat around these pufferfish, and it makes them a little loopy, but they don't, they don't get sick from it, but it makes them look a little silly. And um, tree shrews drink alcoholic fermented, like they eat alcoholic fermented fruits. That's more so just like we think, not on purpose, not intentional, like they're just doing it because it's food. But we do know of primates who selectively go
Mm.
find the fermented fruits and eat them for fun because it makes them a little drunk and a little loopy. So
Yeah.
yeah, they're like, we aren't that different. And I think free will is one of those mechanisms that we use to justify that separation. It's what makes us special. And I think we should be a little more humble and feel special, not because we are different, but because we're the same. I think that's a little like underappreciated nowadays. I think people tend to capitalize a lot on uniqueness rather than being part of a system. I've never seen an ant, right? Obviously, because they're like the little piece of the emergent system, but you never see these ants kind of going their own way and being like, screw all you guys, I'm going to go start my own colony, right? They work together and they build these crazy emergent societies, but this is all based on this idea of togetherness and being part of something, not separating yourself from that thing because you are above it or
Mm.
better than it, right?
Yeah, yeah, that's a really interesting take on that. And I tend to agree with the view that free will is an illusion ultimately. But I think something that freaks people out is the idea that there's no way, if free will isn't real, then there's no way to change ourselves, and we're just at the whims of whatever cultural, societal, genetic influences are playing out in our organism. And
Yeah.
and so, I guess I kind of have my own way of thinking about that, but what's
Sure.
your answer to that?
So I think that's a really good point, that people, when they think of free will, it kind of gives them hope that they can change what's going to happen to them. And I think that there's like a sort of like conflation with of, I don't have free will, therefore I have no control, right? Because that's what, and a big part of anxiety too, and which is so widespread nowadays, is this like idea that I need control or I lack control. And if I don't have free will, then how can I change what's going to happen? Can I become better? Can I like improve myself? um, I think the reason people conflate you have no free will with therefore nothing is changeable and everything is boring. And I think that people should remember that we have no way of knowing what's going to happen. Like I said before, like science is a model of the future, but it isn't the future. Um, and just because you might not have true free will, you still do have that illusion of free will. And so a philosopher can sit around all day and depress themselves by saying, like, I have no free will, I have no control, I am a pure stoic and nothing phases me. I'm like, that's great. Like I see the aesthetic of that lifestyle. But also people can really easily just kind of like drift back into the simulation a little bit. So what you can do is just say, you know what, like, no, maybe I don't have free will, but I feel like I do. And when I wake up tomorrow and I decide what I'm going to do tomorrow, that feels like free will. And roll with it. Roll with it, because that's why it's like that. If humans were built to know everything about free will and completely understand the mind, then we would figure it out, and then everything we did would be dictated off of numbers and models. And again, that's science. That's not real life. Real life is, you're going to wake up tomorrow, and you are going to have goals, but you can change those goals, right? It doesn't necessarily mean, oh, you have free will, so you can change your goals, but you don't need free will to change goals, right? That's will still exists without free will. So you have the drive to do things. Tomorrow, someone can wake up and say, I'm going to quit everything that I've done in life so far, and I'm going to become a photographer. Maybe that seems like free will. What it probably is that they are looking for their goal is, I want to be happy. And whatever I'm doing right now isn't making me happy. But this other thing that I've now aligned myself with, I think will make me happy. That's my next estimate. So it's not that they had free will. All along, they were looking for happiness. And so is that necessary? Is that free will? If you're always looking for happiness, then everything you do is based on that pursuit. So I think that it should be motivational to people that a lack of free will doesn't mean you can't make decisions. It doesn't mean you can't do things, and ignore the fact that it might not be free will. So go be a photographer, go become a writer, or become a scientist, or build a spaceship in your backyard. Like, do these things, not because it's free will, and because it's free will, it's worth doing. It's worth doing anyway. It's just how you look at it, really, that changes whether or not it's. Don't put all your importance in it being free will, and then it'll be important regardless.
That's a great way of thinking of it. That's basically the answer I come to as well. Well, I mean, what a great conversation. It's been awesome meeting you. And I want to pronounce it right. Athanasios. Athanasios.
Athanasios.
Athanasios, damn it. And Athan is kind of the short.
Athan is like the 5-letter, like the summary.
All right. Yeah. And that's a Greek name, right?
It's a very
It sounds very Greek. All right. Well, it's been awesome talking to you. Thank you so much again for coming on and answering all the questions. And I'd love to do it again sometime.
Yeah, 100%. My pleasure. I hope it was coherent. I hope it made sense.
All right. Well, that is it. Thank you so much for listening to or what. All right. Well, that is it. Thank you so much for listening to or watching this episode of Sense of Mind. Be sure to subscribe to the YouTube channel and to the podcast, and also consider giving this show a 5-star rating on whatever podcast platform you use. As always, this channel is brought to you by the Diamond Mind Foundation. This episode was produced by me, Andrew Cooper Sansone. Thank you so much for watching. I'll catch you next time.